One very important thing to understand about evaluating limits graphically is that we're not looking for what the function is equal to at the particular input that we're approaching. What we're looking for is the behavior of that function as we approach that location. I have three graphs displayed on my screen. They all look pretty close to the same thing. They're all relatively similar, but with minor differences. And we're interested in evaluating the limits in all three of these graphs as we approach the value a. Let's start right here with f of x. This red curve is f of x. Notice that this is a very smooth function, and that as we talked about in the last lecture, I can see that as I approach the value a, as I let x approach the value a from both sides, and this is an overall limit, just like we talked about in the last lecture. As we approach the value a from both sides, we can see that the behavior of the function is the following. I approach from that, I approach a from the left, I get this behavior. I approach a from the right, and I get this behavior. And you can kind of see that this function is tending toward the value 3 as I approach a from the left and from the right. So the limit as x approaches a of f of x is going to be 3. Over here in the blue function, g of x, again, I'm interested in finding this overall limit as I approach a from both sides. So that means I'm approaching a from the left and from the right, and I'm interested in what the function is doing as I approach that value. Now notice that this function g of x looks a lot like f of x, except kind of that we have a hole punched out of it. So this function is actually not defined at the value a. I can't evaluate g of x at the value a. There's a hole there. It's missing a piece. But again, we're not interested in what the function is when I evaluate it at that point. I'm interested in the behavior of the function in that region as x approaches a. As x approaches a from the left and the right, what is happening with my function? You can see that if I approach from the left, we have this behavior. I'm approaching there. As I approach from the right, I have this behavior. And so even though my function is not evaluated at the value a, the behavior of the function in that region tells me that the function is tending toward the value 3 as I approach a. So the limit as x approaches a of g of x is the value 3. Now over here in the green function, h of x, same sort of thing, but this function is actually evaluated at a. It looks like the hole that we punched out of the function has kind of just moved down to the value 2. So this function is defined at a, but there's kind of just a disconnected piece. So if I were to evaluate this function, h of x, just write it right here so we have an idea. If I evaluated the function h of x at the point a, I would get the value 2. Because the input of my function is a, if I go straight up, I hit the value 2. But again, we're not interested in evaluating the function at this point. We're interested in the behavior of the function in the region where this point is. So again, if I approach this function from the left and I approach from the right, if I approach from the left, the function does this. If I approach from the right, the function does this. And again, just like the last two cases, I can see that the behavior of this green function h of x in the vicinity of a is 3. So it's important for us to realize that when we're evaluating limits, we're not interested in strictly evaluating the function. The function may not even be defined in that region, but the limit will still exist sometimes. That's all I have for you for this lecture. Look forward to seeing you all very soon.